So the way that we've represented the standard model is with gumballs. Alright, welcome to the long-awaited particle physics lab. I'm going to give you a quick little single-player demo around here today, but of course this is a multiplayer lab, so you can have up to 20-25 students in here at the same time. This is the universe warp tunnel. It doesn't do anything, it's just kind of a cool place to walk through. We've got constructing protons and neutrons in here. Here's the standard model activity. Over there in that room we've got the Feynman Diagram activity. And then behind me we have the Casimir Effect activity, and then the superconductor activity. So I'll go ahead and start with the constructing protons and neutrons room first. In every activity, you're going to be presented with some UI that's going to state the background information of the activity, what we're learning and why we're learning it, right? And then we have the tutorial of the activity, so how you play the activity. Every single station in this room, right, has a particle mixer and a particle recycler. And then to the left of that station is a container for up quarks and down quarks. So I'm going to take an up quark, and I'm going to take a down quark, and I'm going to put both of them into the mixer, right? And we can see from the tutorial that I can make a proton from 2 up quarks and 1 down quark, or I can make a neutron from 2 down quarks and 1 up quark. Let's go ahead and try to make a neutron. So I'm going to put another down quark into here, hit the button, and once it's finished mixing, it's going to give me a neutron. And then I can also see the mass charge spin, as with any other particle that's grabbable in the simulation. But whenever I'm done with the neutron, I want to see how we break it back down. So I'm going to put it into the recycler. And as it goes into the recycler down there, it's going to give me my original 2 down quarks and 1 up quark. But the last thing that I'm going to show you for this activity is going to just be how to make an unstable result, right? So if I put in 4 quarks, we'll see that we get an unstable particle. So over here, right, two down quarks, 2 up quarks gives me question mark. And so that kind of prompts me to be curious about, well, what's that going to be, right? So I get the unstable particle. And when you release the unstable particle, it's going to fly across the room just like that, right? So the way that we've represented the standard model is with gumballs. We have these little trays, and you have to sort the gumballs by their family. So I'm going to go ahead and pull in the lever, and I get a gumball that pops out. And I get multiple of them at once, and it's going to tell me the little symbol for the particle on it. It's going to show me the family color, and then I can also see the mass charge and spin, right? And so I don't know what the standard model is. I've never done or learned anything about this before, but I'm just going to go ahead and try, right? I can see there's quarks labeled here, leptons labeled here, gauge bosons, scalar bosons. So I'm just going to try to put it in a gauge. Maybe this is a gauge boson, right? So I'll put it in, and it's going to tell me what this is. It's going to say muon, heavier version of the electron with similar properties but 200 times more massive, right? So I can read about it, and I'll see in the top, oh, it's a lepton. So let me go ahead and put this in the leptons. And then I get some positive feedback because the background color changed. And so now I know that's correct. Okay, cool. All right, so finally, I've completed all the families, right? So all of the family groupings are going to light up, and it's going to show me what the final output of the standard model is going to be. Then we go to the Feynman activity. So the Feynman activity is cool because we're going to have these little boards here in the center, and they each have these little Feynman pieces, and then we have the diagram models here. Okay, so I'm going to go ahead and start the activity by pointing at it and clicking it. And now that I've started it, it's going to explain to me what the Feynman challenge is. And so let's start the Feynman challenge. Now it's going to give me a random diagram, and it's going to say, create this diagram. Okay, so, and then it's going to tell me, hey, I'm missing 6 letter pieces, 4 miscellaneous pieces, 4 arrow pieces, so let's get started. Because this is over time. Awesome. So I've completed the challenge, and now it'll tell me exactly what it was. So it's a diagram of electron-positron annihilation. Okay. And then I can go play next, and it'll give me another challenge to do. So that's the essence of the Feynman challenge. Now inside the Casimir room, there just so happens to be a boombox. So it's currently muted. Let's go ahead and unmute it. So I can play some songs here while I do these little activities. So there's some sciencey songs here, some classical music, just some stuff to get you into the rhythm. So this one, we have these vacuums here, right? And we see the waves of force in the middle, and then on the outsides of the plates. And what I'm going to do is I'm going to take this lever, and using the lever, I can increase the distance between the 2 plates. And then I can decrease the distance until they're really, really close apart. So what we have here is a magnifying glass, which I can use to get really close in there and try and see the little bit of force that's still going, right? And as we increase the distance between the 2 plates, you'll see the frequency of the force in the middle slows down, and it gets faster, a little bit faster, a little bit faster, a little bit faster, as they get close together. So that's that one. Then we'll go to the superconductor activity. All right, superconductor. This one is probably one of my favorite ones. What we're going to do is we have these 3 cubes, right? And these cubes are grabbable. I can take them and move them around, and I'll be able to see the electrons inside of them scattering apart and return to their original locations within the cube as soon as I stop grabbing it and moving it. Okay. But what we're going to be able to do on each cube is we have this temperature control here, right? Temperature control, right. So I'm going to increase the temperature to make the electrons go faster, and the cube gets more red hot, so to speak. Decrease the temperature. Cube gets more cold. Electrons move more slowly. So they're moving very, very slow until we reach superconductivity. So I'm not going to say much. I'm just going to go in, show you what it's like. So we'll be able to see some information about our mock universe right now. The cosmological constant, gravity levels, just as a general percentage, expansion velocity, dark energy levels as a kind of theoretical state. And then you have a dark energy slider, okay, and a time slider. So this is really to judge what happens over time when we increase or decrease dark energy in the universe. So it's kind of assumed that at this point, we're at present day, right? So this is present day with present levels of dark energy in the universe, right? So we have a sort of normally looking universe, right? The galaxies are pretty close here, not super expanded or anything. But I'm going to go ahead and turn up time a little bit. So as we increase time, the universe is going to expand a bit, but then it's going to start contracting again, right? Because the dark energy levels haven't changed. But if we're a little bit further down in time and I increase dark energy, as I start to increase dark energy levels, and then I give it a lot more time, we'll see things really start expanding out more, right? And we start to get that red shift effect on the galaxies. They're still visible, that is the universe simulation. I can go and press this button again to leave at any time.